Welcome to the SB Grid YouTube channel. Software tutorials by developers, lectures by structural biologists, unique content brought to you by SB Grid.
Hello, everyone. This is Jason Key at HMS in Boston. Thanks for joining today. A couple of announcements before we start our webinar. Upcoming webinars in the SB Grid webinar series. Next month, June 11th, we've got Tomo Dragon. That's Joseph Davis from MIT talking about Tomo Dragon. It's tomography processing software for cryo-ET. And then the last one of the season will be July 9th. That's Dennis Bruckner from Harvard University in the Hextra Lab, going to be talking about his software Match Maps, which is able to match maps from crystals that are not completely isomorphous. So it uses some interesting tricks to match up electron density. So that would be cool to hear about. But for today, it's my pleasure to welcome let me find my window here because I've got my, I think I navigated it away. So it's my pleasure to welcome Darren York. Darren is coming to us from Rutgers in New York in the Department of Chemistry and Chemical Biology. Is that right?
That's right.
Yep. So, and he is going to be talking to us about free energy methods in Amber. So whenever you're ready, take it away.
Sounds good. Well, first off, thanks everyone for joining. I'm looking forward to giving a little overview of some of the free energy methods that have been implemented in Amber recently and over the past couple of years by my group and a few others. So the sort of format of this talk is going to be to provide an overview of the different types of methods for calculating free energy quantities in Amber in different application contexts. But it's going to be methodologically focused. And again, by way of overview, I'm probably not going to have too much time to dig too deeply into any one particular method because there's probably a lot to kind of go over. That being said, if there are pressing questions from the audience, I'd certainly be very interested in engaging along the way. I'll try and stay on time, but I look forward to having conversations either during or after the talk, depending on how things go. So to start out, I wanted to give a sense of, first off, what is molecular dynamics simulation? So molecular dynamics simulation is where we define a potential energy function that's a function of all the XYZ coordinates of every particle in the system, plus any lattice vector information if you're using periodic boundary conditions or other things that specify the boundary. And the idea is that we're going to numerically integrate the equations of motion in order to unfold what we term a trajectory, which is kind of like a film strip of the XY positions of every atom in the system so that we can see the dynamics of the system, calculate equilibrium quantities and things of that nature. So traditionally, molecular dynamics simulations have been focused on watching the dynamics of a single state of the system. So a free energy simulation, now in principle, a molecular dynamics simulation can simulate all accessible states if you have enough simulation time to be able to visit all those states. In practice, however, usually you're trapped in some metastable free energy basin and you're bobbling around in that basin on the timescales that you can afford to simulate. That's why I say traditionally, molecular dynamics simulations tend to sample only one state. Now, free energy simulations are a distinct class of molecular dynamics simulations that specifically target a process where you're changing from one state to another. So this usually requires simulations to be performed at both of the end states, plus any intermediate states that are required to affect the change from one state to another. So usually there can be more than one pathway that connects the states, and part of the game in free energy calculations are finding those ideal pathways so that the differences in those free energies, and sometimes the entire path, can be elucidated efficiently. And so we'll talk about different methods to do this. So the types of free energy calculations that I'll be talking about today are sort of two classes. The first class I'll term free energy surface methods. So here the idea is to explore the free energy of a reduced dimensional set of reaction coordinates that describe the real chemical process that's being happened. So this could be a chemical reaction, this could be a ion moving through a channel, this could be the folding of a nucleic acid or protein. But the idea here is essentially to determine the minimum free energy path. So the reaction coordinates are important. And in fact, usually the goal of the application is to find the minimum free energy path, because that provides insight into the actual mechanism of the process. And so one of the things that can be predicted from these types of calculations are things like kinetics. The second class of free energy methods that I'll be talking about are so-called alchemical free energy methods. Here, the idea is to leverage artificial alchemical coordinates, which I'll sort of generically designate as lambda, where the pathways between two different end states can take a non-physical or alchemical pathway that is chosen to be more convenient than the actual physical pathway. Okay. The goal here is to use these alchemical pathways to compute just the free energy differences between the end states and not necessarily the path in between them. The path is sort of artificial and designed so that the difference between the end states can be computed effectively. So here, thermodynamics can be predicted, but not kinetics. So examples would be looking at things like partition coefficients, vapor to liquids, such as solvation free energies, hydration free energies, liquid like water octanol partition coefficients, things like pKa shift prediction, protein ligand binding, and protein-protein interactions. So those are the two classes of free energy calculations that I'll talk about, and they share a kind of a common fundamental theoretical underpinning. So to sort of get into what that is, I'm going to start a little bit talking about the first class of methods, which is where we're looking at a free energy surface in a reduced dimensional space of reaction coordinates and what those simulations tend to look like. So typically what we do is we use a series of so-called biasing simulations, where the idea is we're going to perform a series of simulations all along the reaction paths. And we're going to use some type of localizing potential so that we can make sure we get the sampling within each region independently. So the reason why we do this is because oftentimes in a pathway, there'll be things like transition states, which are rare events. And if we just waited a long time in order to simulate those rare events, we'd be waiting way too long, and we wouldn't collect the needed statistics to really calculate efficiently the transition state ensemble, which oftentimes are sort of the main goal of the study to begin with. So we use these different biasing potentials, which if they're quadratic are usually termed umbrella potentials, in order to come up with distributions for each segment of the pathway. And if it's a multidimensional surface, then you have to do this in each dimension. So it gets to be a lot of simulations. And the idea is once you unbiased these simulations, you get sort of fragments of what looks like your overall free energy profile. Then you can use statistical methods such as the variational free energy profile method or multi-state Bennett acceptance ratio method in order to piece them together in a statistically optimal way to come up with a smooth continuous surface. So to give you an idea of how this is actually done, here's sort of the process. If we have a free energy, that's the small f, this is a reduced free energy. So it's got KT, units of KT for the energy. So the energy is actually unitless. X stands for the vector of your reaction coordinates. P is a vector which contains parameters for the analytic representation of your global free energy surface. The idea is when you actually do a simulation, what you're going to do is you're going to come up with a set of observed values for your reaction coordinates. That's what this x observed is. And in the end, you can construct an objective function that looks like this equation, which has this configurational integral, reduced configurational integral ZA, which is a multi-dimensional integral over your reaction coordinates of this form. The WA, those are your biasing potentials, your umbrella potentials. So in here is going to be sort of the bias free energy. And over here is any additional restraints that you need to impose on the system that you choose later to remove. The idea is once you've constructed this objective function where you're going to be looping over every simulation, and NA here is the number of observations, the number of snapshots that you've collected for a particular simulation. So you got this big double sum, and in the end, what you want to do is you want to variationally optimize the parameters P in this objective function. Once you optimize those parameters, you now have an analytic representation of your global free energy surface. And it turns out that this is the variational free energy profile method. It turns out the MBAR method works in sort of a similar way, except maybe a little bit less elegant, but it's also a little bit faster. So it's an alternative way of doing more or less the same thing. So I'll just mention now, AMBER has within the AMBER tools that comes with AMBER has a free energy toolkit for performing high dimensional free energy profile analysis, and it's described in this particular paper by Giese, Eckerson, and myself. And so that's something that's a valuable analysis tool when you're interested in constructing multidimensional free energy profiles. However, once you get into high dimension, it's oftentimes not practical to actually compute the entire high dimensional free energy surface. After all, the path through that surface is a one-dimensional thing that could require a whole lot less sampling. So there are a wide array of methods that are focused on going directly after the minimum free energy path in a multidimensional surface. The one I'd like to kind of give you a little bit of an overview right now is called the surface accelerated string method, which is a method that leverages this free energy profile method that I just mentioned before in order to accelerate the convergence of the path. So in general, string methods have sort of the same, have sort of the following format. You start with a guess reactant in product state, and then you come up with a guess path that becomes discretized that connects the reactant and product state. You perform simulations of using biased umbrella potentials along this path, and you watch where the centroids drift away from where they were originally centered. And then what you do is you construct a new path through those set of points, rediscretize it, and continue the process until you converge on the final free energy path. Now, with the surface accelerated string method, what we essentially do is we leverage the fact that we have a method that can quickly compute a robust high dimensional free energy surface locally along the path. And then we can construct sort of synthetic iterations on that path as sort of a preconditioner to be able to accelerate the convergence. Because remember, the thing that really costs a lot in these calculations is when you launch those separate sets of simulations. So every time you launch a set of simulations, you're waiting around for those simulations to finish. The analysis of the free energy surface after that is quite fast. And so if you can leverage that accumulated data that's used to create the surface in order to come up with better and better estimates of where your path should be, you accelerate the convergence. So this is a little movie where what we're going to do is we're going to take a look at a couple of different string methods. The one on the right is our surface accelerated string method. And the first two are methods that have been previously published in the literature. One is a string method in collective variables, and another one is a modified variant of that string method in collective variables. And the idea is we're going to take a look at sort of the convergence of the path. So what we're going to do is we're going to find a path, and we're going to start with two different guesses. One guess of which is a straight line. That would be a concerted mechanism. And another path would be a completely stepwise mechanism. That would be sort of this bottom triangle, if you can see my cursor. So we're going to start with both of those initial guesses and monitor the convergence of the strings to the final path as a function of iteration, just to show how these different things perform. So this is how we evolve. You can see the one on the right converges very, very quickly. The one in the middle converges more slowly, and the one on the left converges the least slowly. But to run that again, keep an eye on the right just to see how fast it converges. This allows us to compute minimum free energy paths for expensive systems. Expensive meaning sometimes when we're computing these calculations, we're using high-level quantum mechanics. It costs a lot of computational time. So the fewer iterations that we get away with in order to get to the path is very, very important in terms of actually being able to do these calculations in practice. So in higher dimensions, this is a different system. This is for the hammerhead ribosome, looking at slightly higher dimensions. We're going to again compare on the same graph all three of those methods just to show what some of the problems are. So what we see, the blue is our surface accelerated string method. The red is a modified string method in collective variables, and the one in green is the sort of the original string method in collective variables. And you can see that the green one gets stuck, in fact doesn't even converge. And this can sometimes happen if you have regions of the free energy surface that have sort of shallow intermediates that the string can kind of get stuck in when it really needs to kind of overcome a local intermediate to fall into the deeper free energy minimum. So in this particular case, it never overcame that barrier. So okay, so that sort of gives a little bit of a summary of some of the free energy methods for computing free energy surfaces and running calculations in AMBER. If time permits, at the end of the talk, I'll talk about the different types of potential energy functions one can use: quantum mechanical potential energy functions, density functional type bindings, semi-empirical, machine learning potentials. But now I'm going to transition the free energy talk to talk about the second class of free energy methods, which are alchemical free energy methods. And alchemical free energy methods are oftentimes used to make predictions about protein ligand binding affinities in drug discovery. And so a lot of the applications that I'll discuss in this context will have that particular application in mind. So to give it a little bit of an illustration of what an alchemical free energy calculation is, first consider the process of binding of ligand 1, where ligand 1 is some drug-like molecule in solution, and it needs to find its way over to a protein, find its way into the binding site, desolvate the binding site, and bind to the protein complex. For drug discovery, oftentimes the goal is to make predictions about which ligands will bind most tightly to the protein. So oftentimes you have a library of congeneric series of ligands that are very, very similar. They might differ by just one functional group or some small chemical space. And the goal is to try and predict actually the relative binding free energy between two ligands. So we could run this process of taking one ligand and have it move all the way over to the protein and look at the actual physical mechanism of how the drug binds and then compare it for every drug. Or we could take a shortcut. We could start with the ligand in the aqueous phase. And if the only difference between ligand 1 and ligand 2 is the change of a methyl group or of one chemical functional group into another. It could be an alcohol, it could be a methyl group, it could be an amine, it could be an acid or whatever. But as long as it's sort of a congeneric series where the drug molecules share sort of a common scaffold, and the only changes are sort of the chemical substituents that decorate that scaffold, then oftentimes a much better way of running the calculations is to alchemically perturb ligand 1 into ligand 2 in the aqueous phase and do the same thing with it bound to the protein complex. And the difference between the free energy of that alchemical transformation in the aqueous phase and protein complex should give you the same free energy difference as the actual binding if you look at this thermodynamic cycle. Except the alchemical free energies are much more computationally convenient to be able to calculate. So it's not that hard to replace one chemical substituent with another chemical substituent, as opposed to looking at the entire binding process. So to give you an idea of how we construct the alchemical free energy transformation, let me start by saying what we do is we define a potential energy that is a function of a coordinate lambda, which will be our alchemical coordinate. So at lambda is equal to 0, we're in end state number 1, which could be, let's say, ligand 1. And for lambda is equal to 1, we're in end state number 2, which could be ligand 2. So the main thing to kind of look at here is what we're going to do is we're essentially going to do a weighted sum of potential energies, where the W0 and the W1 are mixing functions that essentially start to turn off ligand 1, while ligand 2 is being turned on. So if we kind of go to one of these particular energy, the reason why this is a sum over T stands for terms. So what we're really doing is we're looping over all of the empirical molecular mechanical energy terms corresponding to state 0. And so here's a list of the different terms. But that's not so important. What's more important is to understand that there's a further subdivision of the system into 3 regions that we're calling SC, CC, and I. To start with I is the part of the system that doesn't change at all. It's the immutable part. So if we're looking at ligand 1 and ligand 2, then I would be the entire protein and all the solvent and ion molecules, things that are not going to be changing during the alchemical transformation. Now, these other 2 terms, SC and CC, those are the parts that are actually going to be transforming. So assuming you have 2 different ligands, then in essence, the entire ligand would constitute the soft core and common core regions, but it would be split up into 2 parts. What the common core is like, for example, when we were looking at this ligand before, you can notice that everything is the same except the part that's circled in yellow. So the common core would be the part that's not circled in yellow. It would be the part of the system that would be sharing the same coordinates during the transformation, but not necessarily the same parameters. The soft core region, or separable coordinate region, what that is you're going to actually have 2 copies of that. Okay, so those would be essentially reflecting atoms that are sort of disappearing, while another set of atoms are appearing, and they can be different number of atoms. And the fact that they can have separate coordinates, that's called a separable topology. And those 2 topologies don't see each other. So as you're, for example, growing in an amine group, your amine group is not feeling the ether group that's then disappearing. Okay, so that's kind of an important concept in the language of free energy calculations to understand what we mean by the soft core region. That's having something that's disappearing or appearing, being kind of created or annihilated, and it's going to be treated with a special type of potential. Okay, so you can imagine that an atom that whose parameters are just being replaced by something else, it's not really disappearing or appearing. What it's really doing is just maybe changing its van der Waals radii or changing its bond length a little bit. But when you actually have a chemical moiety that's being annihilated while another one is being created, you have to get a little bit more creative about how you switch on and off the potentials to avoid things like blowing up. And so that's what are called soft core potentials. So essentially, this SC identifies the region of the system that will be treated with so-called soft core potentials. Once we have defined this U lambda, I'll just briefly mention there are 3 different ways you can compute the free energy once you've defined your U lambda. One of them is called thermodynamic integration, where the idea behind thermodynamic integration is you're going to do a series of calculations at different lambda points. And essentially what you're doing is you're integrating the reversible work associated with transforming the system from one state, ligand 1, to the other state, ligand 2, both in the aqueous environment and complex with a protein. Free energy perturbation methods, those are a different class of methods that have a different formula, but they're formally the same as thermodynamic integration. You also have to, in practice, run for a series of calculations that connect the end states 0 and 1. And that the reason for that is because in order to get converged results for the free energy predictions, you need to have good phase space overlap between your adjacent intervals. And I'll talk a little bit about what that is. But different flavors of free energy perturbation are designated so-called exponential averaging. This comes from Zwanzig's original equation. But more recently, the statistically optimal approach for being able to compute free energies is using the Bennett acceptance ratio method, or its multi-state variance called MBAR, or termed MBAR. And so this equation down here is the Bennett acceptance ratio method equation, which just sort of statistically balances. What you essentially do is you choose this value of C, which makes this leading term equal to 0, so the numerator and denominator are equal to 1, so we take the log of it at 0, and that comes out to be your Bennett acceptance ratio best estimate for the free energy. There are also the sort of third formulation comes from non-equilibrium work formulations. And the non-equilibrium work formulation is actually a good bridge between thermodynamic integration and free energy perturbation. So the idea behind reversible work, non-equilibrium work or irreversible work, is what you're doing is you're doing a set of fairly fast simulations where what you need to do is you need to first start by doing an equilibrium simulation of one end state. And then sampling that end state distribution, you run a bunch of very short simulations which switch over from that end state to the other end state, but on a time scale that where you can't guarantee that it's at equilibrium. So it's a non-equilibrium switch. But it turns out that if you average over the equilibrium ensemble of all those little non-equilibrium work switches, that'll actually give you an equilibrium property, which is a really amazing result that was derived from Jarzynski and sort of later modified by Crookes. And we use that in the context of our free energy simulations. Okay, so those are sort of the 3 classes of how do you actually calculate free energies, alchemical free energies. What I'll talk about now is how you construct the optimized alchemical pathway and use enhanced sampling to make the calculations practical. So let me just give you a little bit of a sense of the first part, optimizing the alchemical transformation pathway. This is all about trying to stabilize when you're making a functional group disappear or appear. What you want to do is you want to turn things on and off in such a way that that they are stable. And so the after a lot of work, years of work, Right now, what is currently the most stable way of doing that, at least in Amber, is to use what's called a smooth step soft core potential. So what a soft core potential is, so remember, whenever you annihilate a functional group, you don't really make it disappear. Nothing actually disappears. It's not like you take atoms and at the end of the day, they become ideal gas particles. What happens when you make something disappear is you turn off its interactions with the environment. So now the environment can kind of swim on top of the functional group that's disappeared. But also you try to eliminate the interactions within the functional group so as to avoid kinetic traps. And we'll get into this a little bit more when we talk about enhanced sampling. For the time being, let's focus on the interaction of the functional group with the environment. So there's a couple of things that can go wrong when you do that. Like one of the, probably the most common problem is the balance between the Lennard-Jones and Coulomb interactions. So in a real simulation, what normally happens is Coulomb interactions, electrostatics, are trying to associate unlike charges. Positive charges like to get close to negative charges and vice versa. What keeps the positive charges from completely jumping on top of the negative charges is that you have short-range repulsions, which are part of your Lennard-Jones potential. Okay, they're the A term in the Lennard-Jones that goes like r to the 12th. And so it gets very, very steep and repulsive as two nuclei get close together. And eventually that stops the Coulomb attraction from blowing up and having one particle jump on top of another. So when you transform a molecule so that its environment is not interacting anymore, what you want to do is you want to maintain a balance between the Lennard-Jones and Coulomb potentials. Essentially, what you want is you want to turn off the Coulomb potentials, which are the attractive potentials, just a little bit more quickly than you turn off the Lennard-Jones interactions, so that there can never be a crossover point where all of a sudden it's more favorable for the Coulomb interaction to overseed the Lennard-Jones interaction, causing what's called a particle collapse. So we have a functional form that's been shown up here. It's got a couple of key things. One of which is it has a pairwise parameter that's related to the contact distance in the Lennard-Jones potential. It also has a smooth step switching function, which allows it to have smooth transitions endpoints at 0 and 1. So what a smooth step function is it something that goes from 0 to 1, just like a linear curve would, but it does so in such a way that its derivatives at both 0 and 1 are 0. So it starts out with 0 derivatives before it transitions from 0 to 1. And it turns out that that's important to avoid so-called endpoint catastrophes in alchemical free energy simulations. There's also a switching function which allows the soft core potential to become the regular potential as it essentially passes over the non-bonded cutoff. So this allows the soft core potentials to just be computed within the bounds of a non-bonded cutoff, so using the non-bonded list for computational convenience. And then there's a unitless parameter for each one of these potentials that enable the balance between Coulomb and Lennard-Jones to be upheld. So that's what a soft core potential is. I'm going to jump quickly to just basically illustrate that previous soft core potentials that have been developed by others and were implemented in Amber had problems. Every time you see this little circle, that's indicating a point where the Coulomb potential and the Lennard-Jones potential cross over one another, which can potentially cause issues like particle collapse or large gradient jumps. And our potential that we most recently derived and has been implemented in Amber 22 and also Amber 24 has all these stable features, and we haven't yet seen problems. There could be problems, but so far we haven't seen. Related to problems with alchemical transformations, I want to bring up something that's going to come up later called phase space overlap. phase-space overlap is important for the stability of the averages that you need to compute when making a free energy prediction. If you don't have good phase-space overlap, you won't have a reliable estimate of the averages that are needed. What phase-space overlap is it's basically the overlap of the distribution functions. It's a property of a lambda interval. So you have two lambda values. And if you do a simulation at one lambda value, but you actually average the change in energy between end states, and then switch and do a simulation at the other end state, and also look at the same delta U, what you'll end up seeing is when these distributions strongly overlap, that's good for the free energy calculation. That makes the averages in the free energy calculation more stable and your predictions more statistically reliable. Okay. Here, if we look at the free energy profiles, this is looking at the du d lambda, the free energy derivative with respect to the alchemical coordinate. These are using different software potentials, where the one on the right is our latest software potential. But every time you see a little bit of a kink in the profile, that's some type of instability that's usually problematic. If we select 3 examples of this and then collect them and ask, what is the phase space overlap immediately before the kink? What is the phase space overlap immediately after the kink? And what is the phase space overlap right at the kink? You'll see that the phase space overlap always takes a sort of a nosedive wherever the kink is. Okay, so this is just trying to illustrate that phase space overlap is correlated with the instability in the thermodynamic derivative of the free energy with respect to your alchemical coordinate. So it's important to construct alchemical transformation pathways and discretize those pathways so that you always have good phase-space overlap. All right. So now I'm going to move on to alchemical enhanced sampling. And so the idea here is oftentimes in free energy calculations, it's not sufficient to just have a stable alchemical transformation pathway. You also need to make sure that your sampling is such that each one of the lambda windows that you're actually simulating sees the same distribution and sees as close to complete sampling as possible. And so the method that we've developed that tries to do this is called alchemical enhanced sampling. Now, enhanced sampling has a lot of context. Here, really the type of sampling that we want is probably more appropriately termed importance sampling. In other words, enhanced sampling can be good or bad. We want to enhance the sampling of degrees of freedom that are actually affecting the free energies the most, and not artificially inflate the volume of phase space that we need to sample by enhanced sampling other degrees of freedom that are not important for the free energy estimate. So as an extreme example, we don't want to fold and unfold the protein just to enhance sample the binding of the ligand to the protein. Instead, we usually are focusing on conformational degrees of freedom that are directly related to the ligand itself and any amino acid side chains which might be correlated with those different motions. Okay, so we want to focus our enhanced sampling on those degrees of freedom while limiting our volume of phase space by doing more traditional sampling of the other degrees of freedom. So we have a paper out on this back in 2023. Here's something interesting. If we just look at the absolute hydration free energies of some drug-like molecules in the Freesolve database. So the Freesolve database is a database that was collected in a paper by David Mobley, where they looked at a bunch of different and interesting things, and they calculated the solvation free energies using an old version of AMBER. And what we did is we kind of went through and we looked at a couple of compounds that looked a little wonky. And we redid those calculations ourselves. And we got slightly different numbers. But when we didn't use any tricks, we didn't use any enhanced sampling, we didn't use any special potentials or anything, we got errors that were actually fairly similar overall with the errors that were in the Freesolve database, although individual numbers in some instances really differed. And then we redid things using enhanced sampling, using RepWave exchange with solute tempering, such as in the FEP Plus program from Schrodinger, except it was our implementation in Amber, so it wasn't exactly the same. And that significantly improved the solvation free energy. So this was all using like the GAP2 force field, and all of this is using the same program, the same force field, just setting up the system and doing the sampling different. When we use the ACES approach, which is our version of enhanced sampling, the errors dropped even more than with REST2. And it turns out that that REST2 and ACES are mutually complementary techniques. So you can use REST2, you can use ACES, you can use both at the same time. And so if we used REST2 and ACES together, it drops a little bit more, but essentially it's the same as ACES. So the REST2 on top of ACES didn't do too much. But that just goes to illustrate, even for calculating an absolute solvation free energy, sampling is very important when you have drug-like molecules that have multiple rotatable bonds that influence the actual solvation free energy. So to give a little bit of a sense of some more recent studies, we applied ACES to ring flipping in the SARS-CoV-2 main protease, some main protease inhibitors. And I wanted to show an example of where the inhibitors differ by a ring, a 5-membered ring that's attached by a single bond to a common molecular scaffold. Okay, and what can happen, okay, is if you have a part of that ring that, for example, donates a hydrogen bond. Usually that hydrogen bond might, for example, be hydrogen bonded to the backbone of the protein in order to facilitate a more stable contact. If you change that hydrogen bond donating into something that doesn't donate a hydrogen bond, so for example, a methyl group, or even if you just took away this hydrogen so that it was no longer a hydrogen bond donor, but rather a hydrogen bond acceptor, then one of two things would happen, okay? If you did a regular calculation and just did that transformation, what would normally happen is that would kind of cause that ligand to start to become ejected from the pocket, because now all of a sudden there's not this hydrogen bond donating group. Instead, in this particular case, there's a methyl group. So there's a steric group that's pushing the ligand away. However, if you just flip that ring around by 180 degrees, that would position that methyl group away from the pocket and replace it with something that did not have a steric repulsion. So it turns out that that's the preferred orientation of this ligand. When you take the hydrogen and instead grow in a methyl group, it causes the ring to flip. So here's the basic idea. If you actually needed to simulate the physical process of that ring flipping, then it turns out that ring flipping has a pretty high barrier, and you tend to not sample any ring flips in a normal simulation. But with enhanced sampling methods that treat that entire ring as part of the soft core region, the ACES method is essentially able to annihilate the ring that's in one conformation and replace it with a ring that's almost isosteric with, for example, the methyl group in a different orientation. So instead of simulating the process of ring flipping, instead we have two rings, two copies of the ring. One of which is in the syn orientation, and the other one of which is in the anti orientation. And we simply make the syn disappear while the anti appears. And we can sort of tunnel through the barrier associated with the physical process of ring flipping. To illustrate that, just in the context of a regular MD simulation, if we take a look at these different ligands and ask the question, what do the torsion angle distribution profiles look like if we performed just a regular MD simulation, departing from an initial structure where the conformation was anti versus whether the conformation was syn? So anti is in black, syn is in red. And what you can see is that distributions sometimes are quite a bit different. In the case of ligand 21, when we start with the syn orientation, it stays in syn. When we start with the anti orientation, it stays in anti. Whereas with the ACEs method, regardless of whether you start with the anti or syn, you get back the same distributions. So the ACEs method is going back and forth between syn and anti using this alchemical coordinate to tunnel through the physical barrier of the ring flip. Okay. In the context of free energy simulations, I'll just state that it does two things. It improves the sampling and increases the accuracy of the actual conformational flipping distributions. So it gets the right distribution of the ring flips. And when you turn around and compute an actual free energy from that, what ends up happening is that the statistical error estimates for the free energy is much better using the ACEs approach than other methods. And the reason is because it's sampling those distributions in the right ratios as opposed to sort of getting stuck. So ACEs enhanced sampling will essentially improve the precision of the free energy estimates and also their robustness. Okay. So now we've talked about optimized alchemical transformation pathways, and we've talked about the ACEs method. One of the things that we didn't talk about is, remember, whenever we do the ACEs method, or actually any of these alchemical transformations, we have to choose a bunch of different lambda states. We can't just go from one end state all the way over to the other, because that will be, very poor phase space overlap for usual calculations. So usually what we need to do is we have to compute many different states. However, when we do many different states, it may be that certain states have poor phase space overlap, while other states have very good phase space overlap. And of course, the phase space overlap will be critically dependent on how close in lambda space the 2 points are. So what we can do is we sort of note that if we monitor the phase space overlap of two ligand transformations, 18 to 21 and 19 to 21, using different sort of schemes for specifying the lambda points. So like a linear scheme would be just to start with 0 and take equal spacing of lambda points all the way until you get to 1. GW and GL are both using so-called Gaussian quadrature to decide where to place the lambda points in order to improve the numerical integration when you end up integrating it using thermodynamic integration. The only point of this slide is to demonstrate in the top row what we see are what are called the Hamiltonian replica exchange acceptance ratios. So whenever you use a method like ACEs, one of the things that happen is you don't do independent simulations at each lambda limit. What you do is you do all the simulations at the same time, and every 20 steps or so, you take neighboring simulations and you ask the question, can I swap the two coordinates in a way that obeys Boltzmann statistics? So you use a Monte Carlo criterion to ask the question, can I exchange my coordinates so that I can mix the states between this lambda state and the next lambda state? And by doing that, you not only enhance the sample across the lambda dimension, but you also ensure that each lambda state is in equilibrium with all the other lambda states. However, this only works if you actually exchange coordinates. So if the difference between this lambda state and this lambda state have such big differences that whenever you do this Monte Carlo test to see if you can swap coordinates in a Boltzmann consistent way, If the answer is always no, that means you have a very small or non-existent replica exchange acceptance ratio. So if you have a 0 or very low replica exchange acceptance ratio, you're not actually enhanced sampling because you're not doing these critical exchanges, which are the foundations of your enhanced sampling. So the point is that replica exchange acceptance ratios are very important. And to make a long story short, they're also correlated with phase space overlap. So we've put together a method where what we can do is we can do a short so-called burn-in simulation where we do a simulation for only maybe a couple hundred picoseconds. And from the replica exchange statistics, we can construct a two-dimensional map from which we can make a prediction about where the optimal lambda spacing would be in order to make the phase space overlap uniform and maximized for all lambda points. So we call this the optimum phase space overlap method. And here are some examples of some different schemes. So the linear in GL, this is the linear lambda spacing and the Gaussian quadrature spacing. And what you notice is that the phase space overlap and the replica exchange ratios kind of have a pretty deep minimum. They get pretty close to 0 here in the middle, and they get much larger at the endpoints, whereas the optimum phase space overlap is more uniform. So the dashed green line is the predicted phase space overlap based on that short little burn-in simulation. And the black line is the actual phase space overlap when you go back and actually do the simulation. And the red line is the actual replica exchange acceptance ratio, showing that it is also much more uniform when you optimize the phase space overlap. It turns out there's different. So if you end up going back and looking at your replica exchange statistics, one of the things that you can measure with replica exchange is how often the same coordinates go all the way from lambda 0 through all the lambda windows all the way to lambda 1, or a round trip where what happens is you start at one lambda window, you go all the way to the end, all the way back, and then back to your original starting point. That's called a round trip. Both of those are important for enhanced sampling, and when you use the optimum phase space overlap method, then you get a lot better replica exchange statistics, a lot better enhanced sampling, which is one of the underpinnings of the ACES method. So there's different variations of this. It turns out when we wrote the paper, we were focused on phase space overlap, but in the same paper, we also talk about a slightly different index that's more directly related to replica exchange, which is this column on the right, which is a little bit more stable than the other variants. This is the actual one that we're promoting. You get almost identical results for all three of them, except when these other methods sometimes go bad. This replica exchange acceptance ratio method seems to be much more robust. So the last thing that I want to say is when we analyze the system, when we do our free energy analysis, when we do our MBAR analysis, we don't analyze each thermodynamic perturbation one at a time. Instead, what we do is we do the entire network at once. Because one of the things that's important is that when you have a so this is showing here on the right is something that's called a thermodynamic graph. And you'll notice that there are multiple ways to connect different ligands. And in fact, you can trace the different arrows and actually come up with various cycles where you go from one ligand to another ligand to another ligand, and you end up with the original ligand. Whenever that happens, that's called a theoretical cycle closure condition. And theory says because the free energy is a state function, if you ended up where you started with, the free energy should be 0. Well, it turns out in the actual calculations, they're not 0. But when you analyze the results, you can constrain the free energies so that all of the cycle closures are obeyed, and you can make much more robust predictions about the resulting free energies when you do things on a network-wide scale. So it turns out that this is a form of Bayesian optimization where the constraint conditions are formulated as priors, and they don't have to just include cycle closure conditions. If there are known experimental free energy values, the analysis can also involve experimental constraints, which sometimes, as is kind of illustrated in this bottom right, when we include a small number of experimental constraints, in this particular case, just one, sometimes we get correlation with experiment for all the ligands that's much higher than if we didn't include the constraint. So importing into the analysis a little bit of known experimental information sometimes can increase the predictive capability of the rest of the network, including those ligands which were not known. So I have another section that I could have talked about that concerned machine learning potentials, but given the time, I'm going to go ahead and stop here, and I'm going to skip to the end and recognize the people that really did all of this work. So I'm going to get right to the conclusion slide. I have a fantastic group that involves several talented graduate students, postdocs, and senior research professors, all of which have been working together towards a common end of creating rich infrastructure in Amber to perform a wide range of free energy methods that allow us to look at problems of enzyme design and drug discovery. And so they're really the ones that are responsible for all these innovations. They're listed here: Tai-Sun Lee, Shulman Eckerson, Tim Giese, Ryan Schneider, Yujin Tao, Suchen Tsai, Jinxi Zhang, Shi Zhang, Erica McCarthy, and Lauren LaRue. So thanks to all of them, and I will be happy to take any questions.
Fantastic. Thank you very much. Questions, you can send them in the Q&A. I think the Q&A button should be available to everyone. I think you may also be able to send chat.
I'm trying to figure out how I can see the chat.
And then I think there's also a reactions button. If you want to raise your hand, see, I can raise my hand like this. I can call on you, we can unmute, we can, and you can ask your question directly if you prefer. I mean, I have a couple of questions just to kick it off. Just basic question about like alchemical transformations. What are the limitations between sort of core and transformed groups? If you're going to annihilate a group in a ligand, what are your, like, how much can you annihilate before you blow up? Maybe this is a bit of a naive question. Maybe it's context dependent. I'm not sure.
Yeah, so it's a bit of a loaded question in the sense, I mean, we're still, given these tools, we're still establishing a lot of sort of the best practices in order to how to use them. In some sense, you can annihilate an entire ligand if you do it slow enough. And so by doing it slow enough means it'll require many different lambda windows in order to affect that. And it turns out usually when you do that, there's an order to things. Like oftentimes you start to annihilate things that are at the extremities first, and kind of make something shrink into something smaller and smaller before it disappears, as opposed to taking the entire thing and just having it fade away, if that makes any sense. Yeah. And so usually taking an incremental approach where you're doing it in that way. That being said, there are different sort of tiers of complexity that I didn't really get into, but sort of the described in this little review, sort of the hierarchy is the tiers of complexity involve, well, when compounds share a common molecular core, then calculating the relative binding free energies is going to be the most stable, because you have small functional groups that are differences. So always with free energy calculations, half the art of this is trying to formulate the question so that you're going to get an answer to a question that you can actually that's actually computationally convenient to answer. And so when you have a congeneric series of ligands that only differ by small functional groups, doing relative binding free energy. So, but the relative binding free energy calculations, really require that, other than the functional group, that the scaffold still maintains the same binding mode to the protein. If it changes and all of a sudden comes over here, then this won't work. Because essentially what you'd be doing is making one thing disappear over here and another thing up here over here, and that will introduce complexities. So if you have compounds that have different molecular scaffolds, but still occupy, so what I mean by when I say molecular scaffold, what I really mean is more or less for the scaffold, there's a direct atom to atom mapping. This atom goes into that, this atom goes into that atom, so on and so forth. What I mean by different scaffolds is when that's not clear. Like maybe you have a 5-membered ring and a 6-membered ring, or something of that nature. So there's not necessarily an atom by atom mapping, but those things are still kind of on top of each other. That's what I mean by having the same binding mode. So it turns out that you can still use sort of a counterpoise thing where you make one ligand go away as the other ligand appears, as long as they're really overlapping in terms of their binding mode. That's what we call the core hopping BFE. We're counterpoised, absolute binding free energy. The most complicated case is when you have two things that have different binding modes. So there's no advantage of making, I mean, you can imagine, if you make something disappear as something else appears and they're both on top of each other, that's going to cause minimal perturbation to your environment. If you make just something disappear, your environment is going to relax, you're going to have solvent that goes, you're going to have to simulate the time scales and calculate the free energy of all those processes. So the hardest is when you have different binding modes where essentially you have to sort of suck it up and perform absolute binding free energy calculations, because there's no advantage of trying to do something relative simply because their volumes are not overlapping. There's no sort of benefit on sort of minimizing the perturbation in the environment by doing them at the same time. Usually doing them at the same time is actually adding insult to injury. It's more of a perturbation than doing one at a time.
So, but computationally, in terms of adding, just the cost of the computation, adding in, 1, 2, 5, charged groups, hydrophobic groups, like adding in that complexity, does it lead to linear? Is it not, what is the cost computationally to do larger permutations? Because again, like it makes it harder to achieve those narrow slices, right? So you're
yeah. So it would be more or less linear with respect to the number of atoms that are being perturbed, in the sense that if you do things one at a time, well, so all right, let me answer this a little bit more carefully. If I were to just run the calculations in a way where I'm sequentially eliminating different chunks of the molecule of roughly equal size, then one could argue the computational cost of doing that is going to be linearly related to the size of the perturbation. However, I can guarantee that by doing that and by propagating the errors, it's not like doing that is going to lead to a statistical error estimate that would be at the same tolerance level as if you did just one perturbation. Yeah. So if you actually wanted to ask the question, what would that calculation cost to do it at a fixed precision level, then it would be actually non-linearly, because the bigger perturbation would actually require quite a bit more sampling in order to get to the same precision level. So I think the non-linearity comes in that sense. But I think, unfortunately, when you read the literature, and you look at free energy calculations where they report error estimates, it can sometimes be a little misleading, because statistical error estimates, if you do error propagation, and you're looking at variances and things, That's all great. We do that all the time. But they can be misleading because those statistics only report on the fluctuations within the free energy basins that you actually visited in the simulation. And they don't know about any free energy basins that you might have completely missed. And so oftentimes, if you go back to those thermodynamic graphs and ask the question, okay, they reported, statistical error estimates of 0.3, 0.5 kcals per mole. What were their errors in the theoretical cycle closures? If I went from A to B to C back to A, and oftentimes those numbers are, factors of 2, 3, 4 times larger than the reported error estimates. So those are real errors. I mean, it should be that if you did an exact calculation, if you come all the way back to what you started with, you better get 0. If you don't, then that's an issue. And so we're an academic group, right? And so we actually like problems that where something wonky happens. So oftentimes we construct fairly dense thermodynamic graphs that have a lot of redundancy so that we can check these thermodynamic cycles in kind of a rich way. And in some cases we have enough redundancy. If we find a problematic edge, we can kind of sever that edge from the thermodynamic graph and just ignore it because we have enough redundancy elsewhere. In real drug discovery applications where, the computational team needs to come up with their predictions by Thursday in order to have a discussion with the synthesis team, they don't have to, they oftentimes don't have time to do all this academic messing around and figuring out why this cycle didn't close, right? And so there's where I think, so that's one of the reasons why we developed, also these cycle closure methods in the analysis part to enforce the cycles to close, which at least will get you a little bit step closer to the truth than if you didn't do that. It also allows you, as you accumulate data, like oftentimes in different cycles of lead optimization, you actually make the compounds and do measurements. Maybe it works, maybe it doesn't work, but now you have that added information. Why don't you include that same ligand in the next round, even though you know what the answer is, but constrain that'll also give you a constraint that might help to improve the predictions of the things that are now unknown.
Yeah. Well, that gets to one of the questions that we just had. One of the questions in the Q&A here is that, so you've got, a binding pocket. That pocket could be rigid. That pocket could be flexible. You've got induced fit, preformed pockets. In the context of these alchemical transformations, what are the sort of challenges that presents in the calculation of the ligand conformations and binding energies?
Yep. So here's an example. Oftentimes, if you have a ligand where, let's say you have 2 ligands, and the binding modes of these 2 ligands also are coupled with the change of, for example, rotamer state of 1 or more side chains, then you could imagine that could be sort of a difficult process to compute, where if you had to sort of simulate the physical transformation of all these different rotamers. Essentially, what the ACES method will allow you to do is actually include the side chains as part of your transforming region. Now, they're not the ligand side chain doesn't transform into something different. What it does is it just transforms the ligand side chain in rotamer 1 into the same side chain in rotamer 2. So what it really is doing is trying to sidestep the conformational transition from rotamer 1 to rotamer 2. Instead, it's making rotamer 1 disappear as rotamer 2 grows in. At the same time, the ligand disappears, and the other ligand that has a conformation that's more supported by rotamer 2 grows in. So it's kind of this almost tunneling effect that's fake, because we're using this fake alchemical transformation in order to affect it. But in terms of sampling, it helps. So the ACES method allows you to define an ACES region that may include part of your protein target if the conformational degrees of freedom there are in distinct states that are not easily interconvertible within the timescales of the simulations. And typically, these simulations are like damn short on an experimental timescale. So they're 5-10 nanoseconds. Which is, but of course, you're doing like maybe 500 of these simulations for 5 or 10 nanoseconds because you're doing a bunch of different windows and a bunch of different Huygens transformations.
But certainly on that scale of like sidechain movements, and that's it. Like you're not going long enough to see anything other than some rotamerization of some side chains and maybe some functional groups, but that's backbone changes and those sorts of things are sort of not within the scope. With that, thank you very much. It's fascinating, amazing work. It's really cool to see. Amber is certainly foundational to like many of the tools we use, everything from like drug discovery to minimizing NMR structures and everything in between. So it's an amazing package, and
My pleasure, and just for you and also the audience, so it would be we're open for collaborations. This is a great group to talk to. We're a very interactive group. I got a couple of my group members also on this call. So if there's any follow-up from anyone that wants to talk about specific applications or have a follow-up discussion, we would be delighted to entertain those conversations.
Oh, fantastic. Thanks. That sounds great. All right. Well, thank you again. And thank you everybody for joining.